Now I'm recording. So today is mainly about IoT and continuing the last time. But I had a few slides left over from the last time. So before going into IoT stuff, I will repeat some of the previous slides here. And then at 11 o'clock, we start with a discussion with the poster project, and probably there will be a break in between here because we are waiting for Mats to arrive for that. So it will be 11 o'clock and not earlier. And you can sign up for lab groups now. It's on Canvas. But last time we talked about real-time stuff on field buses, and there were some small things remaining here. I think I'm not really sure, but I think this was the last slide I did. Yes, so we were talking about real-time and Ethernet. And there are non-real-time, soft real-time, hard real-time, very common. And to achieve hard real-time, you need special hardware. The normal hardware is not enough. That's the idea with these classifications here. So if you use normal Ethernet, normal TCP/IP, you cannot guarantee that packets arrive in time. There can be queue buildups and delays that you cannot really control. But with special hardware, it is possible. So that's really the idea with these things. And one of the more maybe interesting or popular hard real-time Ethernet standards is one called EtherCAT. And that's, also from Germany, Beckhoff Automation, second largest behind Siemens. And and the EtherCAT is it's related to Ethernet, and it uses some Ethernet hardware, but it's kind of quite different. So it can handle a lot of communication with very hard deadlines and quite fast. So the thing is that EtherCAT is very often used as a ring network, and that's a bit strange. That's not the usual thing. If you look at Ethernet, you have typically this star topology where you connect everything to switches and routers. And EtherCAT is really fast due to a good idea here that each slave is connected in this ring and that it's special hardware. So whenever data is received, it is immediately transmitted again. So there is no software or program involved buffering the packets. The hardware forwards all the bytes in the packets directly. So that means when you start sending a packet, it starts sending it across the whole ring at the same time. And then, so all slaves will get the packet very, very quickly. And that means and the packet has some kind of address, addressing it to a slave 2, for example. And that means that the other slaves will just don't care, and only slave 2 will actually read the packet and buffer it for the software. So so it's really fast times, and you can also you typically have one master, and that means that you will have no strange things happening. You will have no competing traffic or queue buildups. So you can guarantee that whenever you send a packet, it will quite immediately be received by all slaves. So fairly simple, but very fast solution. Yes. So yeah, some things nice to know about cables when you deal with networking is that sometimes you need this termination resistor. And this resistor should match the resistance should match the cable impedance. So that means when the signal arrives, it will notice no difference in impedance. So it will just be received and not reflected. Otherwise, you can get a reflection, and then you will get disturbances in the signal and, well, maybe not be able to read it or receive it. So these termination resistors is quite important. And this is an example for the Profibus. The reason you cannot have two long wires is that the signal gets filtered in a wire. You can regard a normal wire as connected capacitors with resistors in a row like this. So the capacitance need to be charged. So the signal, when a high voltage arrives, it will cause this capacitor to slowly charge. And that goes for the whole wire. And the resistance here makes the charging a bit slower. So you have some kind of delay. So if you input a very square wave, at the end of the wire, you will have a very slow rise because all the capacitance needs to slowly charge. And at the same time, when you, well, similar, when you turn the signal off here, it will be a slow decline because all the capacitors slowly discharge. And it's really small, picofarad, Alice writes. Yes, that's true. It's really small capacitance. Farad is the thing you measure capacitance in, and pico is really, really small thing. It's smaller than micro and nano. And that's per meter. So when you have very long wires, you get quite a lot of capacitance. So that's the reason you cannot really have two long wires, because the signals will get disturbed or filtered. And that has to do with the time as well. So if you have a higher frequency here of signaling, you will get into more trouble because then the capacitance will slow it down. So there is a maximum frequency depending on the length of the wire. Yes. So, and the resistance, resistance in the wire also makes the signal be lower in amplitude. So that's also a problem. The signal gets weaker if you transmit over long distances. But the capacitance is maybe a bigger problem because that stops you from going fast. Yeah. And one very common problem when you deal with communication is also interferences, electromagnetic interferences. And there is a term called EMC, electromagnetic compatibility or something. That's the testing procedure you typically use on equipment to prove that they are insensitive to interference, that they can handle interference. But there are a lot of different sources of these induced interferences. That is, if you have a equipment or wire, they can be affected by other radio transmission in the room or neighborhood. They can get affected by transient things like thunder, lightning. ESD is the charge up you have as in your body. If you touch the wire, you can accidentally kill it, the equipment. You can cause a high voltage spike. And you also have transients, voltage transients from machines like this kind of motors. When they start and stop, it's quite common that they induce quite small but very high voltage spikes in the electricity network. And you also have our normal power networks. If you have a power cable, it's 50 hertz in Sweden at least. And that's some kind of electromagnetic radiation, almost like normal radio, which can actually be picked up by a wire and induce current and voltages in the wire. So yeah, so there are a lot of ways of disturbing equipment and communication. And one very common way of coping with these things is to use a twisted pair cable. And this figure tries to explain why a twisted pair cable is good. Because here you have a transmitter and a receiver, and you have a power line here inducing alternating current 50 hertz voltage on the communication wires here. But one trick that is very common is that you use a twisted pair cable. You send the signal on two wires and one of them is inverted compared to the other one. So if you want to send a 0, 1 here, you send us a 1, 0 here, low and high voltages. So this is the real input signal you want to transmit, but you transmit it on one wire and the inverted signal on the other wire. This means that when you have this induced interference, it will interfere in the same way on both wires. So if you add a certain number of volts at a certain point, you will add it to both of these wires at the same time. And that still keeps the difference in voltages between these wires, because at the receiver end, you only care about the difference. You don't care about the exact voltage levels. So and this is an example of an isolated receiver where you have a light emitting diode and a photoresistor of some kind. So you get galvanic isolation. You have no electricity here, only light. And that's a common way of blocking interferences on the receiver end. Then you will not, if you have a bad voltage spike in here, it will not destroy the receiver equipment. And also these light emitting diodes, the LEDs here, the lamps, they are connected between these wires. So, and that means they are not connected to any ground or something, no reference voltage. So they light up depending on the difference in voltages between these two lines. And you have one forward and one backward connected. So this one lights up when this is high and this is low. and this one lights up when this is high and that wire is low. And it's insensitive to these disturbances because that raises the voltage on both wires the same amount, and that will not affect the voltage difference here over the LEDs. So this is a very common way of constructing communication wires. You have twisted pair, you have this inverted signal that makes it insensitive to many disturbances. Yeah. So, yeah. Okay, so that was some wire knowledge and technology here. I think we try to go back to today's agenda. It was supposed to be about IoT and continuing the industrial communication stuff from last time. But it will also be a little bit general about IoT here as well. And I think you all heard Andreas last week or last week telling you about Industry 4.0, and it's very much related to this IoT stuff. So yes, let's see. Yeah. Just a reminder, there are material to read. These two papers are kind of good to read for background and information about industrial communication. Andreas probably showed this picture. It's a little bit about IoT and how it affects all kinds of different sectors in our society. And sure, it's factory automation is one part with a smart factory, but you also have IoT in all kinds of things like smart cities, smart hospitals, smart highway, and things like that. And the basic idea with IoT, Internet of Things, is to put out sensors everywhere and collect data. That's the very common way of looking at it. And so we have sensors, we have communication, very often wireless, and very often also sending data to some cloud service, some kind of platform. And the ideas here are many. We should get smarter everything. Cars should talk to each other and talk to the smart city. And everything should be more automated in some way and more efficient. And it goes over all kinds of sectors: smart home, elder care, medical, healthcare, transportation, manufacturing, smart city, energy, all sectors in some way. And there are some new possibilities. Some have been thinking about some kind of new possibilities here. And you can get more efficient, like if you have more data collection, better data, you can save resources. For example, you don't need to empty a trash bin when it's half full. You can automatically order or do it when it's full, really. So you become more efficient and saving resources. You can improve automation. Your fridge can automatically order milk, for example. And that's a smart home, but you also have the same examples in the smart cities and factories and things. One part is the localization positioning thing. If you have GPS or sensors everywhere, you can more easily embed them into all kinds of things. And maybe in the future, you can ask some system where you put your screwdriver, where in the home, which room is it in? These kind of small things. but factories or shops can use it to track merchandise, cars or customers maybe. So there is a lot of possibilities here. And when you collect a lot of data, you might also get new insights, this big data area. For example, if all cars shake at the same spot on the road, maybe there is a damage at that spot. So that's one way of maybe getting new insight by collecting a lot of data. Yeah, so that's a little bit about what IoT is about. And why do we have IoT today? Well, it's possible thanks to a lot of improvements. So we have better batteries, more capacity in batteries. We have the normal computer evolution with smaller transistors, higher integration, leading to smaller systems. We have invented a lot of new sensors, and we can make them small and cheap. We have better wireless communication, and in some way we have also better protocols and software today. So all these things together make IoT possible today. I usually show this picture. It tells you really a lot about the development of semiconductors. In old time, 1970s, we had quite few transistors in the processors. Today we have billions, so we have 10 or 20 billion transistors. So this shows the possibility. And when the transistors have been, they have shrunk and become smaller, and that means they use less energy and actually can run faster as well. So you get less energy and higher performance on smaller chips. And for IoT, this is important, not because you can put in 10 billion transistors in a high performance processor, because if you use the same technology now, you can put, for a small system, you might need only 100,000 transistors, and that will be really, really small. The area on the silicon chip is for 100,000 processor is hardly visible, and it uses very little energy and has still high performance. So you can build really small systems with these small transistors. And one example of a sensor is like this. You have a micro electromechanical sensor. That is, it's a MEMS. It's a quite interesting area where in mechanics and electronics, where you build really small sensors in a similar way that you build a processor visible on the left here. So the same factory technology can be used to build really small sensors here. And this is packaged in a larger sensor together with a processor that handles some computations. So it's kind of a smart sensor. From the outside, you have a more you have an easy to use sensor chip here, but inside it's this MEMS element as well as a processing element here. So you have everything integrated quite tightly here. And so it's a micro electromechanical system. And this is the inventions that make sensors small and cheap, really. Yeah. And one thing that is important as well for IoT is the wireless communication. And here you have really a jungle of technologies today, and many are competing. So the future is kind of unknown here. So there are a lot of different technologies, and we can start by looking at the next slide here from this link. It shows an overview of all, some of the competing techniques today. So we have, for short range, we have the normal RFID NFC techniques that we have in our phones for contactless payment and things like that, and also in our credit cards. The RFID is the credit card stuff, and NFC we have in our phones. It's more, but they are similar. We have the local area Wi-Fi, but also some mesh routing protocols like Zigbee or Z-Wave. We have Bluetooth Low Energy. That is one of the newer Bluetooth standards. And we can see here that range is longer and we can get higher bandwidth. But on the larger area, we enter the mobile phone networks. So they have longer ranges and quite good bandwidth. But here, in the IoT sector, there are actually a lot of competing technologies here. Two of the more larger competitors are LoRaWAN and Sigfox. And LoRaWAN exists at many places in Sweden, actually. And even Trollhättan kommun has a LoRaWAN network, actually. And it's quite different from the telephone networks. They have a potentially very long range and can typically focus on sending small amounts of data, a few bytes from sensors spread out, maybe, for example. But also competing with these, which is kind of commercial protocols, we have the RTEM and NB-IoT, which is part of the 5G standard. So that's IoT communication for the future mobile network in some case. But this is also existing techniques running today. So, and they actually compete with these commercial networks. So, well, we have an unclear future here, really. Wi-Fi is trying to invent some new higher range stuff, and then we have satellite networks, space networks, that also kind of tries to cover some ground. Yes, so I back to this Bluetooth comparison here. Let's see if we can open this IoT radio. This is a good overview here, I think, for some of the techniques. So here we have all kinds of use cases, and this overview has kind of pointed out where do these different technologies fit. So they think Sigfox is good for these things, LoRa in the middle here, and LTE, that's the 4G network. It's not the modern 5G, really. So we can see that all kinds of use cases maybe fits different techniques here. But it's quite impressive. We have meter range for the Bluetooth, but for this LoRa and Sigfox, we actually have quite very long rural, outside cities, we have actually 30 to 50 kilometer range. That means it's very easy to build these networks. It's cheap to put up antennas, base stations. So you can cover a lot of area, really. But when we look at the performance here, what can you do? Well, it's kilobit per second. It's like 300 bits per second here. And here we have 140 messages per hour, which is 12 bytes. So it's meant for sending kind of sensor values, reading the temperature or something and sending it some once a minute or something maybe. And if we look at Bluetooth, shorter range, we have quite a good bandwidth. And for the mobile network, you have quite much better bandwidth actually. So, but then you have some other drawbacks here. It's more costly energy-wise. And there are difference. The mobile networks, kind of tricky. You need a SIM card, you need subscriptions. These are sometimes, they have other business models around them, which can affect really how you can easily build large networks with a lot of sensors. Okay, so some of the techniques existing here. And this is an example from Ericsson as well. And they actually focus only on mobile network, like telephone network communication, and especially 5G, which they think should cover everything. So in the future, 5G will be able to do everything, they think. And it might be a good bet. So they have these use cases like smart metering, asset management, keeping track of things, fleet management, cars, drones, VRR, automotive, communication, traffic safety control, smart grid, the energy network here, robotics, and advanced automation and control. So on the right side here, you have more time-sensitive traffic, deadlines, hard real-time, industrial automation. Here, slower but critical IoT, more bandwidth required in broadband IoT here, massive, you have really no law, it's not any deadlines or hard, it's very slow, but you have millions of devices maybe. So, and I think that really everything should work here. The 5G new radio should cover the real-time traffic as well as the critical. Broadband IoT is also 5G new radio or 4G, little older networks. And here for the massive IoT, they are competing using the NB IoT and Cat-M protocols, which is included also in the 5G. So they think they cover everything with the 5G, really. And I think 5G can be really more and more pervasive everywhere in some years. If you combine the wireless and the communication stuff, you get kind of wireless sensor. And this is one example you can buy. It's quite big. It's meant for developers trying out stuff. But the interesting thing here, I think, is that you have actually more than 120 possible sensors to try out here. You need different kind of sensor boards, but it's really a lot of different strange sensors. You can sense everything today almost. And also, I think is kind of nice is that this card can handle 16 different radio technologies. That is, the manufacturer of the hardware choose not to choose. So they include everything. So they don't care which wireless technology will get dominant in the future. They will handle everything. That's the idea. So here we have, it's a slightly older system. We have 4G, 3G, probably 5G in the future, LoRaWAN, Sigfox, and all kinds of Zigbee, Digimesh, yes, Bluetooth, everything. So that's typical. You have sensors, you have computation, and you have a lot of wireless communication. So you get some very effective wireless sensor. You know. Yes, 120 and 60. So I was planning to show my favorite example here as well. It's something showing what you can do. And this is a bit old technology now, but this is a company tracking birds, and they have, as an example, been tracking white stork using a small IoT device on the back of the bird here. So it has an OrniTrack 30. It's a 30-gram weight tracker. So they can actually follow the bird when it flies from Lithuania down to Africa during the winter, and then back for the summer. And then in the summer, they can follow it in Lithuania when it starts nesting, building its home in the middle here and fetching food and material. This is a very small device, solar powered. So they have a very small battery that during the day it's charged, and during the night it loses some charge here. So it's good that the bird is outside in the sun. Otherwise you get no energy. And they have really small systems. The smallest one is 9 gram. So it's very lightweight. You can put it on small birds, and they don't use so very fancy. Well, they have 4G wireless communication, and they have a GPS, so they can get the position, some small memory. The wireless technology is kind of old, but and they sometimes can use SMS messages as well. Probably that will change in the future if you get more and more 5G spread across the world. Sensors, accelerometer, magnetometer, temperature, so they can actually, except for the location, they can actually measure the acceleration when the bird flies, direction, which direction is it heading, and temperature data as well. And this is typically what we find in our mobile phones. These sensor chips are so spread and cheap today, so you could put them in everything for almost no cost. So sensors are easy. Data collection, storing data, and sending data are kind of more expensive. But this is a good example of what you can build, a very small system tracking stuff. And yes, and what do they sell? They sell these systems, but of course they also sell a cloud service as well. That is service which handles all the data and creates maps and things like that. So, and that's, I suspect, a very important part of their business model, not only selling the transmitters, but also selling the services, the cloud system services. Yes. So smallest unit is actually 9 grams today. This is old. So that's kind of interesting. And here you see some of the one typical things that you very often find also is over-the-air updates. So that's kind of funny. You can update the software in the thing over the air. That is when the bird is flying over Africa, you can update its software. And that's something you typically want to do because developers are a bit lazy, or they find bugs, they find security risks, something. So software is very often updated. That's a typical case. Okay, I will start looking at industrial IoT, but I think most people are falling asleep, so time for a break and some coffee, I think. And I will pause the recording here. So, okay, so we have IoT, and we also have industrial IoT. So IoT is the general thing affecting the whole society. And of course, in industry and manufacturing are one important part of the society that also is affected. And there is a term called industrial IoT, and that's really how can IoT be used in industry. And there is a industrial internet consortium. It's not IoT, but it's internet. But they deal with IoT as well, so they have a definition of industrial IoT systems here. It's a bit vague, but it's really control systems in industry that contain sensors and actuators, large complicated systems, and these are standard, but they connects and integrates with enterprise system, business processes, and analytics, collecting data. So it's more often integrating the machines with the back-end systems in some way. If we take a look on the industry consortium here, here is how smart is your factory, but we can take a look on industries here. We can see that it's not only manufacturing. There are many different kinds of industries. So we have the energy sector with our electricity delivery, healthcare, hospitals, mining, retail, that is our shopping centers, and smart cities and transportation. So they actually cover quite a lot of use cases and things here. So that's the idea. They have a lot of nice use cases. So I put this link at the bottom here, which is quite interesting actually for this course as well. And for you, you can get ideas for maybe poster subjects and things. So here we have different use cases. You can read about things they have done. Here it's the energy sector, quality assurance, something, manufacturing, monitoring, healthcare. So they have a lot of different examples of stuff here. And so this is quite interesting. So unexpected design. Oh, I haven't seen everything myself here. Energy peak savings, that's the energy sector. If we look at a use case, it's actually sometimes you have articles to download, and sometimes you should contact one here. Maybe, oh, boring. Well, I think you can find quite a lot of need credentials. Oh, you need to log in to get access. Okay. There are use cases public that you can read about and things, but it seems to be a bit mixed. And also one of the articles, one of the 2 articles that you should read contains these 5 use cases also for industrial communication. And that's quite interesting because it gives an example of what are they aiming for. And this is the 5G that tries to handle all these communication scenarios here. So in the first use case, they look at time-critical process control inside factory, very fast communication with hard deadlines, and they think 5G would fit here. For example, between a PLC and a robot, you could use 5G maybe. I'm not sure, but that's one of the use cases here. And then you have non-time critical, that is slower stuff like tracking objects, data collection, and things like that. So this is inside a factory. Then you have remote control. You can be off-site, for example, very useful in the mining industry, where you want to remote control machines maybe. And then you have inter-enterprise communication, that is tracking goods, interconnection of different premises, different buildings. So that's more data needs to be sent further. Then you have an interesting new thing that's connected goods, that you actually keep track of all kinds of goods during the whole world. And maybe it's being sent from the other side of the earth, and you want to always know where it's located. And this can also track connected stuff at customers. When you buy things, you can still have connections to the manufacturer, so they can collect data, for example. So this, some example of use cases here as well. I think I had this picture for a typical industrial, industrial manufacturing or control system. You have the machines, robots on the right-hand side, and then you have more supporting systems and economy and resource planning systems here. And in between you have the SCADA system, supervision, control, and data acquisition, and dashboards and controlling and getting information of what's happening in the factory. And one idea with this industrial IoT is really that you start to move things or change things here. So there is a trend of moving all kinds of things, administrative things, and also dashboards and supervision to the cloud. And there is also a trend of getting new technology here. For example, the normal Ethernet or internet protocols and more wireless protocols to get introduced in these old-fashioned field buses and things like that. This is, of course, a bit controversial. Factories are very often vulnerable to security intrusions, or it should be reliable. It's very often very secret information due to the competition. You don't want any competitors to know what you're doing. So moving systems to a cloud environment might be a bit complex, because you're afraid that it's easier to get security breaches maybe, or can you trust the cloud operator, really. But it's very common. We saw for the bird tracking system here that you buy a sensor and you automatically maybe buy a cloud service as well. And I think that will happen in the factory as well. You buy a robot with some PLC or something, and then included in the package is a cloud service from ABB or something. So you need no other computers maybe. You only need a PLC robot and a network, and you are up and running. So I think things are moving to cloud because it's cheaper, really. So I think that will, and more flexible way of developing applications. Yes. So are there new protocols? Well, there are some new things happening in industry, and this is an overview of IoT connectivity standards. So it's industrial IoT, but we recognize really many of these protocols. It's standard IP and TCP UDP. And you have standard Wi-Fi or normal Ethernet connecting things, but you also have different maybe mesh wireless systems or mobile phone systems, and also maybe new Ethernet technology in the form of TSN, these time-sensitive networking that also tries to are introduced as new standards. But also there are some inventions on the top of the stack. You actually the normal HTTP protocol for web is actually, well, a bit heavy, so there are alternatives like MQTT and CoAP for sending data. And you also have on the more middleware application level here, you have, for example, OPC UA, which is a data exchange, object-oriented data exchange and subscription framework in some way, distributed framework. I think, yeah, these are the things I mentioned here. So there are some new things happening and new protocols arriving, which we will typically find in the factory communication, in the future at least. I think it's all these things are fairly new. Well, on the cloud end, how all the big actors like Microsoft, Google, Amazon, they are actually focusing also on the IoT business area. And all these actors have services today where you can collect IoT stuff and data from IoT devices, and they store it for you, and they make nice dashboards. They can use AI, machine learning to analyze your data, and also integrate it with other systems like business systems or resource planning systems. So this is a quite big business area. I think Microsoft sees this as a very important area for the future. And if we go to Azure Microsoft Overview IoT here, we can see how does the front page look like here. So you can see that they are actually, data everywhere. They want to collect things, but also get insights and act on the collected data. So, and they try to cover all kinds of industry sectors. And they have a lot of services. They want you to buy everything. And actually it's kind of, it's probably quite good, but very often you pay per byte of collected data or something. It's different payment models, but sometimes you pay for each collected byte or something. So yeah, so we can see that they are really want to get into the area here. When you do cloud, you also end up with some problems sometimes, and that is that cloud might be too far away. If you have a data center in the US and collect data in Sweden, it's a little bit clumsy. So you get kind of long latencies to move data far away to cloud. So one thing that's important is the internet edge, and Microsoft also has edge solutions now. So the idea is that you extend the cloud in some way to edge devices. And what does that mean? Well, it simply means you have a computer very close to you, maybe inside the factory or your home, and it says Microsoft on the box, and it's connected to Microsoft's cloud. So you administer it in the same way as you kind of administer the cloud services. So it's an extension of the cloud in your home in some way, or in the factory. This means that you can have a more smooth transition. You can choose to do data collection that only goes to the edge, and then you run computations and aggregate data and just send some of the data to the real cloud, maybe. And that gives you quicker responses, lower latencies. You have more bandwidth available. You can reduce costs of sending data to the actual cloud. So, and you get security as well, and maybe privacy. So you can stop data from leaving your factory. So the internet edge is becoming more and more important. And you talk about edge computing and fog computing and things like that. Yes, there is a Swedish company you can look at called Crosser, I found. They are really pushing for edge solutions and selling kind of edge boxes. Yeah, IoT influences a lot of old systems. So there is some problems today with the IoT. For example, if you look at software developers, all systems now are internet connected. So they are more vulnerable to security breaches. And you have these over-the-air updates as a standard today. And that's not familiar, especially to old software developers. They are not used to thinking about network security. So you get breaches like the Mirai botnet in 2016, where some kind of botnet was created using normal web cameras or surveillance cameras. And it was a stupid thing. It was just an easy password or something. It's some simple thing to break into a lot of cameras and use them, connect them as a botnet to attack other internet sites. So that's an example of developers really neglecting all kinds of security, and it's mainly clumsy or kind of ignorance. So the development of these IoT systems are a bit different. Then you have the internet, which is actually affected by the IoT as well, because the number of devices increases, and you really get a problem with the old IP numbers. And maybe IP version 6 will save us here. Using IP version 6, you get really a lot of IP numbers. So each IoT device, billions of devices could easily get IP numbers. So it's not happening. You typically can manage with older IP version 4 and using a lot of gateways and address translation. So it's we'll see. But IPv version 6 is actually a good idea. And the internet edge is becoming more important. And you actually get more connection between edge sensors and cloud environments. So it's not as easy to just put up a firewall and stop all traffic if you have a company. You really want a lot of traffic going through from all sensors and things. So that causes a kind of difference. And you have the edge fog computing, that the cloud is extended in some way to your own site. In the factory, you get some new protocols, cloud connections, and you try to reuse Ethernet networking. And this emerging standard is interesting, the time-sensitive networking, which you can read about in one of the articles. So there are a lot of challenges here. If you want to be busy and work in the IoT area, you can focus on security. That's a very important issue. There is a joke that says that security is the letter S in IoT. And that's very funny because there is no letter S. There is no security. So that is a problem. Privacy, misusing data. How can you protect all our data to be misused? It's a large interoperability problem. When you buy a bird tracking thing from the bird tracking company, it's very hard to use connected to some other cloud system or something. You need to buy the service from the same vendor. So it's interoperability standards are kind of lacking. Safety might always be a problem. Systems shouldn't harm you if it's safety critical. And also sustainability, semiconductors in everything. We kind of pollute our environment. If you have 1 million sensors spread out, can you really take care of them? Given 10 years age, can you collect all the 1 million sensors, or are you just spreading semiconductors everywhere? Yes, Terminator. Don't build a Terminator. That's not good. And you have a lot of technical challenges, like in the details. Data storage, energy, communication, that's kind of normal things. So there is a good book. If you want to read more about IoT, it's not very expensive. It's a Swedish guy called Oscar working in the area, and we are considering we should actually include this book, I think, as a course literature, maybe next year. But it's not required reading. But if you really want to read more about IoT, I think you should look at this book. It's not so heavy. It's quite an easy read. Okay, that was the general plan of today. A little bit about industrial communication and especially the IoT. And you will get more wireless and radio communication from Mats later in the course. But now I think we go for a break until 11. Then we start with some information for the poster project. And sign up for the lab groups. Yes, do we have full groups here now? Oh, okay, no. Still plenty of room in the unpopular group, I see. Yes, that's good. So, yes. Yes, now it's time for you to build Terminators. That's good. No, Yes, if there are questions, otherwise we go for a break and start again. I think I put 11 sharp. Yes, 11:00. So it's 11 o'clock precisely. We start with the poster information and things. And hopefully we have a Mats arriving as well. We'll see if Mats shows up. But break until 11.